we're asked to calculate s prime of 2, which of course is the derivative of s at 2. We have the formula for the derivative of a power function. The derivative with respect to t of t to the n is n t to the n minus 1. Okay, we saw that in our preceding class, and we applied that to several power functions. Okay, now, using the d dt notation for s prime, we see that the s prime of 2 is going to be d dt of s of t at t equals 2. Now, that doesn't mean we're going to put 2 in for t here. We're going to find the derivative of s of t, and then we're going to substitute 2. So, and we're ultimately going to find that s prime of t is 0.06t plus 2. And it's fairly easy, and with a little practice, extremely easy to determine this. So, and then we're going to plug into this, and we're going to get a value for s prime of 2, and it's going to compare very favorably to a value up here. Now, s prime of t, well, I'm going to say that's derivative with respect to t of s of t, just a different notation for s prime of t. And this notation is a little more convenient for finding the derivative of this s of t function. So, knowing what we have seen about derivatives, we know that the derivative of this plus this plus this is the derivative of this plus the derivative of this plus the derivative of this. Also, that the derivative of 0.03 t squared is just 0.03 times the derivative of t squared. Any constant multiple of a power function, the derivative will be that constant multiple. The derivative of that multiple will be that constant multiplied by the derivative of the power function. And whether that makes sense or not, we'll see how that applies. So, first, the derivative of 0.03 t squared will then be 0.03 times the derivative of t squared. And we write that as 0.03 times the derivative with respect to t of t squared. And then the derivative of the 2t is going to be 2 times the derivative of t. 2 times the derivative with respect to t of t. And then the derivative of 9 is going to be 9 times the derivative with respect to t of 1. Now, I wrote it this way simply to put this into the context of the power function rule. And we do have another rule that says the derivative of anything that doesn't change is 0, because the derivative is the rate of change. The number 9 doesn't change, and it doesn't care what the value of t is. It's always the same, so it's unchanging. So its derivative, which is the rate at which it changes with respect to t, is 0 still. I've written it this way just so we can apply this rule. Now, so we have 0.03 times the derivative with respect to t of t squared. Is t squared a power function of the form t to the n? Well, yes, it certainly is. For what value of n? Stop and think. Don't just wait for me to tell you. Well, if n equals 2, then t to the n is t squared, and t squared is, of course, what we want to take the derivative of. So the value of n is 2, so we put in the value of n here, and we get 2 times t to the 2 minus 1. So it's 2 times t to the 2 minus 1. And then, of course, that's multiplied by our 0.03. Here, is t a power function? Is it of the form t to the n for some number n? Well, people were pretty quick to say, yeah, t to the 1. T is the same as t to the 1, so n equals 1. So what's the derivative of t to the 1? It's 1 times t to the 1 minus 1. 1 t to the 1 minus 1. And then, is 1 a power function? Is it of the form t to the n for some number n? And the answer is yes. T to the 0 is 1. So this is t to the 0. So the derivative is going to be 0 times t to the 0 minus 1. That would imply that there's a negative 1 power of t, which there isn't because of the 0. So, and of course, 9 times 0, t to whatever, is 0. As soon as you have a 0 in a multiplication of a series of numbers, everything is 0. So this term gives you 0, and I can kind of say that as this is 0, so it's not going to be represented over here. Now, 0.03 times 2t to the 2 minus 1, well, t to the 2 minus 1 is just t to the 1, which is t. 0.03 times 2 is 0.06, so this term gives us 0.06t. 2 times 1 times t to the 1 minus 1, well, t to the 1 minus 1 is t to the 0, which is just 1. So this is just 2 times 1 times 1, which is, of course, just 2. So we've calculated that s prime of t is 0.06t plus 2. You'll see other examples of polynomials, and it's always very easy to take derivatives of polynomials. With a little practice, you can just about do it in your sleep. All you need is this rule and the practices we've done here. In fact, we can pull the constants out and stuff like that. And the derivative of this plus this is the derivative of this plus the derivative of this. You'll see those rules more formally, and we've already talked about them. Okay, so it follows then, if s prime of t is 0.06t plus 2, then s prime of 2 is 0.0 times 2 plus 2. We replaced t in s of t with 2, so this t will be replaced by 2. So we have 0.06 times 2 plus 2, which is 2.12. Now let's compare that with some of the numbers we got up here. Do you see anything that seems similar to 2.12? Well, yeah, we actually had 2.12 up here before, but I've included the next couple of significant figures, the 0, 3 here. I was tempted to do that before, but I wanted to double check my calculation. Seemed obvious. 0.01 squared is 0.0001. Multiplied by 0.03, you get a bunch of zeros and a 3, and it lines up like this. Okay. Well, the point is that when we have a 0.01 second interval, the average speed for that interval is very, very close to 2.12. And if this 0.01 was replaced by a 0.001 or 0.0001, the result would be a number even closer to 2.12, to the result that we get from the derivative. And the reason is that the limiting value of this process, we keep letting this number here, and of course the denominator, the 0.01, gets smaller and smaller and smaller. Then this number is going to approach this number as a limit. And of course we prove that algebraically by taking the limit as t goes to 0 of s of t plus delta t minus s of t over delta t, simplifying it, taking the limit, and getting the general result. And that result will match this. That result will match the derivative. So the reason we start by evaluating these difference quotients and their limits is because the limit gives us, first of all, the limiting process gives us a formula for finding the derivative, and the derivative is the limiting value of change in s divided by change in t.